Well, thank you so much, everyone, for joining us today. And Brian and I would love to tell you a bit more about our journeys of deploying Istios and operating this service mesh platform at Snowflake and some of the interesting challenges that we faced and how we solved them. Um, so the two speakers here are Brian and myself, Charles, and here are how you can find us on the internet. Both of us work on the container platform teams, and the service mesh is a indispensable part of the container platform. Just a quick overview of the agenda today. We will start by introducing what Snowflake really is, because some of the infrastructure challenges comes directly from the Snowflake products and serving the products based on this multi-cloud need. And then we will tell you a bit more about our container platforms and service mesh and what are the sets of technology that we use and what is its current scale, etc., and a very high-level overview of the architecture and technology. And then we will dive deep into the challenges that we faced with Istio, specifically with multi-cloud, multi-architecture, compliance, and lifecycle management. And lastly, we will talk about the future roadmap we have in mind, some really exciting features that we wanted to do and implement in the coming quarters. So Snowflake brands itself as the data cloud. Although it started as a data warehouse business, nowadays it does everything data related. And what's interesting about Snowflake is that it sits on top of the three major cloud providers, which means its data capabilities is also multi-cloud or cloud agnostic, if you will. And because of the Snowflake product is multi-cloud, it means our infrastructure also has to be multi-cloud. And one interesting challenge that the container platform team faces is that how can we develop or design our infrastructure and systems to be as cloud agnostic as possible, so that it's easier to operate and easier to extend and build additional features on top of it. And Snowflake is now available in multiple cloud and multiple regions around the world. It depends on our customers and business need, and we are still on a hypergrowth mode and expanding into new regions and potentially into new cloud. And a bit more about our container platforms. It's based on Kubernetes, and nowadays we have 140 clusters. And because of the rapid expansion, we expect to build a lot more in the coming quarters. So on the right-hand side, you will see a chart that shows the growth of the number of clusters over the years, and it's definitely a hockey stick exponential growth mode. And because of this growth and the expectation of this growth continue in the future, we have to invest heavily in the toolings and automations. Right now, in steady states, we run about 4,000 nodes or 80,000 containers across these clusters, but these clusters autoscales and depending on the incoming traffic. So in and this is sort of like an average state. And we use the cloud provider managed options for Kubernetes control plane, so the EKS, AKS, and GKE. But we develop a lot of custom add-ons and our custom policies to really make the platform multi-cloud and multi-tenant to make it really user-friendly. And like I said, Snowflake presents in multiple regions, so our clusters are also regional to be more fault tolerant, and it's around the world whenever Snowflake product has a presence. And the platform is multi-tenant in terms of both teams and app, so multiple teams can share the same container, and they, I'm sorry. multiple teams can share the same cluster, and the isolation boundary is mostly based on namespace and namespace resource quota and a bunch of policies based from Istio or network policies, etc., to ensure high isolation boundaries across different workloads. And lastly, it's integrated with our legacy VM-based infra. Snowflake is founded in 2012, and that's before Kubernetes was available. So we still run some workloads on VMs, and we need to ensure that containers can interoperate with those VM-based infrastructure. And Brian, why don't you tell us more about what Istio is and why is service mesh useful?
Sure. And just I'll give you a heads up, Charles, when we can go and move on to the next slide. But okay, thank you everybody again. So let's talk first about what a service mesh is. We briefly mentioned Istio earlier, and Istio is more or less the implementation of a service mesh, but why would we want to use one anyway? So a service mesh, for those who are unaware, is a dedicated infrastructure layer that you can add to your applications to more or less transparently add types of capabilities like traffic management, security layers, observability, without having to add them to your own code base. And the service mesh is more or less the pattern of which you would do to achieve these types of capabilities and delegation to this infrastructure layer to achieve those means. In the case of Istio, we achieve this through a couple of different components. There's this what's called the data plane, and the control plane. With Istio, we'll talk about those in just a little bit, but with Istio, we get a lot of things out of the box that are very useful for our container platform. A couple of those things being secure communication between services via mutual TLS. There's strong identity-based like authentication and authorization. There's just tons of nice features out of the box, like automatic load balancing for different protocols such as HTTP, TCP, gRPC. There's also automatic metrics that we receive and logging for all the different incoming and egress traffic into our applications. And lastly, like there's very nice features you can implement for your traffic coming into your applications, like fault injection, traffic shifting, mirroring, all these nice capabilities that you would otherwise have to build by hand inside of your application in one way or another. So Istio itself runs inside Kubernetes, and if we take a look at the diagram here, we can see briefly how it's implemented. Istio works off of what's called a sidecar injection model. So every single application will automatically have a proxy attached to it. Istio's proxy of choice is Envoy, which is a layer 7 proxy that can be used to implement all these types of things we just mentioned. And every tenant we have within our clusters will have this Envoy proxy attached, usually by default. And all these Envoy proxies that can communicate with each other more or less make up what is known as the data plane. The Istio control plane, or otherwise known as pilot, is what is responsible for updating all of these proxies with different configurations, such as what load balancing rules service A should have the service B, what retries behaviors should they have, as well as important things as certificate issuance between services so they can communicate with each other through mutual TLS, as well as being able to have proxies automatically discover each other without having to codify that within your applications. So there's also, you can see here within the graph, the diagram, excuse me, that we have metrics that become available automatically through each individual envoy, such as simple things like request durations, how long the request counts, all these types of things that we would get out of the box that we can ingest into our telemetry dashboards and things like this. Charles, could you go to the next slide? We can talk about what it looks like in our infrastructure layer. So this diagram gives a nice high-level view of what our Kubernetes clusters typically look like in terms of our configuration with Istio. Most just in every cloud provider, we have a layer 4 load balancer that traffic will hit from external clients. We decided to stick with using layer 4 instead of layer 7 since we already have layer 7 at the Envoy layer when we eventually route traffic there. And at all the layer 4 load balancers will more or less pass on that connection to a thing we have not mentioned yet, which is the Istio gateway. The Istio gateway is a special version of Envoy that is running and receives traffic from the load balancers. That this the Istio gateway's job more or less is to route traffic to other proxies within the mesh based on specific criteria of the requests, such as things like the host header, the paths, also things like this. And we use this as a mechanism to have a single point of entry into our cluster and dynamically route traffic to the appropriate upstream services responsible for receiving traffic. You can note here that the traffic between Istio gateway and all the proxies are done through mutual TLS, and similarly, traffic between containers are done through mutual TLS, which is all generated by a certificate that IstioD creates. You can optionally create your own root certificate, but you can get one out of the box through IstioD. A couple of things to note here. We try to implement zero trust. So by default, services are split across our clusters by namespace, and namespaces cannot talk to each other by default. Additionally, we do not allow tenants to have access to endpoints outside of the cluster by default. There are mechanisms through Istio which you can implement this egress access, and similarly have communication with other namespaces inside the cluster. I would call out with the egress access that Envoy, or Istio rather, is not typically meant to be used as security ACL-based solution for controlling what can be accessed outside of the cluster, because there are ways to bypass Istio proxy, but this is one way we do try to restrict access to tenants. And then you can see here at the bottom, Charles mentioned our VM layer that we allow access to through another load balancer. Okay, I think that probably provides a quick brush through of what we have. One thing I'll call out here regarding the Istio gateways, because we're going to be talking about this shortly, is that the Istio gateway and our Istio-D are running on dedicated worker nodes that are isolated from the rest of our infrastructure. We decided this early on to have the control plane and the ingress layer running on dedicated nodes so we can size those appropriately depending on our ingress needs. I think we can go ahead and onto the next slide, Charles. Okay, so over the next couple of slides here, we'll be talking about the different challenges we've run into while running Istio. The first one, probably being the most pressing one, is how we can actually auto-scale that ingress layer safely. So as I just mentioned, the Istio gateway is responsible for receiving traffic from the load balancer. We currently implement this by, well, let's take a step back here. So one thing that's important for us right now is that we preserve the source IP address for services coming into our clusters and for traffic that's hitting our backend services. And there's tons of different use cases for doing this. One that Charles will talk about briefly soon is rate limiting. So maybe we want to rate limit based on client IP. We need to be able to maintain that IP at the ingress layer so that we are able to capture that before Istio makes a decision whether to send that traffic to an application. There's also network policies we may want to enforce, like allow listing based on IPs. And there's also just internal use cases where we want to have the source IP. Source IPs can be preserved in a couple of ways. One of the more common ways is through a particular field on the Kubernetes service object called external traffic policy. There are two different values for this. There's one that's set to local, and there's one that's cluster IP. If you run it with cluster IP, you can basically guarantee that no matter which it does not matter if the node that you're sending traffic to from the load balancer has Istio running on it or the Istio gateway running on it. It will forward that traffic to another node, which does. The problem with running it in that mode, though, is that kubeproxy is going to do source NAT translation on that request, and you will lose the IP in the packet along the way, which causes a problem for actually knowing what client actually sent that request. So right now, to work around this, we run our load balancers with local node set. This does require, though, that basically every single node which you run that particular service on, in this case, the Istio gateway, has a gateway pod running on it. And right now, we run our load balancers with the worker nodes, which run Istio gateways on it as the targets, not the pods directly. So that means we must always guarantee there is at least one Istio gateway pod on each node. This can be achieved in a couple of different ways. You can either run a gateway as a daemon set, or you can run the gateway as a deployment with strict pod anti-affinity requirements to basically schedule it across different hosts. So this is how you can more or less achieve client IP preservation for incoming traffic. This works very well for us right now, but it does present problems when you start to try to autoscale the gateways. Could you go to the next slide, Charles? Okay, so scaling up is actually very simple to solve. You can add new pods to new nodes via a pod autoscaling if you're using a deployment controller, and node autoscaling via things like the cluster autoscaler, which will dynamically scale the number of worker nodes based off scheduling constraints. Scaling down, though, is challenging to do safely, and this is specifically because we are trying to preserve the source IP. So the problem that happens is during node termination, or pod termination, excuse me. When you are trying to terminate a pod, there is no coordination to remove that node which is running the pod from the load balancer prior to the pod being terminated. So this means if I do like a pod deletion request for Istio gateway, I can end up in a situation where I'm still sending traffic to what the load balancer detects as a perfectly healthy node. And this will continue typically for up to 20 seconds, depending on the cloud provider's health check implementation. It varies by cloud provider. Most of the time, though, I think all the time, you cannot configure it to be close to 0. So this more or less means you will incur a downtime when either you're scaling down, doing worker node operations to replace the worker node, things like this. And from the client's perspective, they will see either connection resets or we'll get a 500. So this means we have to have some sort of process to handle the safe termination of the pod and coordinate the teardown of that node such that the node is always removed prior to the pod being terminated from the load balancer. And I can talk in the next slide, Charles, if you may, a couple of ways to achieve this. Okay, so one nice thing that's been coming out lately is that cloud providers are starting to support sending traffic directly to pods instead of the worker nodes which are running that particular pod. Unfortunately, not all cloud providers offer this at the layer 4 level, but what this looks like is effectively you have a controller inside your Kubernetes cluster which is listening for pod creation or deletion requests, and on those API requests, it'll automatically interact with that cloud provider to delete or remove the pod as a target from the load balancer. And it is actually automatically address the ordering issue here of making sure that you have deleted the node from the the pod from the load balancer at this point first, prior to the pod being terminated. Again, though, not all cloud providers support this functionality, so we are currently going with this approach. One other way to approach this is to more or less implement your own termination handler to make sure you safely tear down the pod. The way that you can do this in Kubernetes land is this nice field called or what's called a lifecycle hook. And there is this lifecycle hook which you can execute prior to pod sig kill, which is called a pre-stop hook. And basically you can run any set of commands you'd like on that pre-stop hook. And what you can do here is you can actually intentionally fail your Istio gateway pod's health check so that the pod will start failing any health check endpoint call from the load balancer. And what you would do in this situation is call the health check fail endpoint and then sleep for some period of time in the termination handler so that the pod sticks around long enough that it'll actually fail the health check on the load balancer, and then it can continue to process any remaining requests that it has open until the pod is eventually terminated. And that can be left to your desired behavior. This is probably a nicer option for those who want to do something that's a bit more agnostic and can use already Kubernetes primitives that are available to implement this behavior. And then lastly, there's one other way that we've explored in the longer term is to actually move away from kubeproxy, which is more or less causing the source of this trouble of performing because of the SNAP translation it's doing when there's not a node available on that node. Excuse me, there's not a pod available on the node to receive that request. There's an interesting project called within Calico where you can use Berkeley packet filter to basically remove the need to do this SNAP translation and then have requests be forwarded over to other nodes safely and still preserve the client IP. We're barely exploring this option, and it's something we're looking at doing in the future. We're excited to see if this will work out for us. But one of the downsides with this is that this implementation is not currently available on ARM worker nodes. And you also typically need to install some specific binaries for eBPF to work on the worker nodes, which you may not be able to do if you're using a managed worker node implementation. Okay, well, I think that's all I had to say on this particular challenge. I think, Charles, you can go ahead and hand it off to you.
Yeah, thanks, Brian. I can talk about the second challenge that we faced with Istio, which is rate limiting the incoming requests and prioritizing the different types of clients on the same host. So we have a cluster-wide rate limit service based on Redis, and this is opt-in only, so it's not turned on by default to services running within our Istio service mesh. And the opt-in is available by applying to Kubernetes API this Envoy filter object. This is the pretty standard way that a user can extend into could extend the Istio offerings and capabilities by patching the Envoy sidecar configurations. And how it works is that once the client opt in to this Envoy filter or the rate limiting features, the client requests that hits the Envoy sidecar. Well, first prompt the sidecar to check with the rate limit service, which will make a rate limiting decisions. And the rate limiting service will check the Redis data store to see how much requests has been coming in lately from this particular client. And then once the rate limit decision is made, the Envoy sidecar could decide to drop the requests or proceed by forwarding this request to the actual upstream backends to process it, and then forward back the response to the actual client. Having a rate limit service within our cluster is useful, especially for services that has multiple replicas. The alternative of rate limiting solution here is to make the rate limiting decisions locally at the Envoy sidecar level, which is easier and get the jobs done. But when you run multiple replicas, you kind of want to sort of coordinate between the entire set of replicas to make sure that the rate limit policies is consistently applied. So when the incoming request hits the second request hits a different pod, we do want the second pod to be aware of the prior spike or surge of requests hitting different nodes or different pods. So this is why it is useful. Now, the rate limiting scheme I just described doesn't really solve the prioritization problems because our platform, including the VM-based infrastructure, is multi-tenant. What that means is that there can be multiple workloads or multiple clients/servers running on the same source host, and we need to differentiate the priority of different workloads based on business needs and business criticality. And that means for high priority workloads, we don't want it to suffer from starvations from noisy neighbors. So noisy neighbor is a metaphor that refers to other workloads running on the same hosts, but is making a ton of requests, which means that neighbor is depleting most of the rate limit quota on this particular hosts. So that's why the business critical workloads sharing the same node might be starved from the rate limit requirements. The short-term solution that we put together is to use a custom HTTP header from on the client side. So what that means is we will instrument the clients with a service header, and the service header's value will be set to what exactly this client or the application's name is. And then we will patch the client's Istio proxy's HTTP filter with a Lua script. I'm sorry, this patching is actually done on the service side so that we can extract this custom HTTP header called service. And then based on its value, we can set specific rate limiting policies or decisions based on this header. And Lua script is one way to extend, or is another way to extend the Istio sidecar capabilities. For anything that's more complicated extension logic, we should probably use the WebAssembly because it supports multiple language and also has very nice support for testing. But because of this service header is something very simple, so we think Lua script is something that's pretty productive and easy to maintain. And next, I want to tell you more about a third challenge that we faced, which is with Istio version upgrades. And like any software, there's only a window of support in terms of every version. And eventually it falls out of the support window and you kind of have to upgrade. It's the same story with Kubernetes or other critical infrastructure software. And for Istio in particular, upgrade has to be done more often. The reason is that for each minor release, it is only supported up to 6 to 8 months after release. So it's relatively a shorter support window. And also there are frequently security patches, and some of them are pretty severe vulnerabilities. So we want to get on the latest version as quickly as we can. And that's why we need to do the upgrades more often than we would for, say, Kubernetes cluster upgrades. Now, like I mentioned, because we run 140 clusters nowadays and expect to build a lot more in the future, upgrading all of the clusters manually is tough and very error prone. Doing so would require custom toolings and automations for sure. And we will also need to validate the new version of Istio before shifting all the workloads over. And we also want to revert quickly if the upgrade is not successful. So all of those are just trying to mitigate the possible outage or disruptions in our production environments. So to achieve that, the best practice is to use what we call a blue-green upgrades. And I would love to tell you more about the specific steps that we do within the blue-green upgrades scheme. So this diagram shows what we would have right before the upgrade, assuming that we are running Istio version 1.9. So as you can tell, the control plane, or the Istio-D, and also all the Istio proxy sidecars within our cluster is running version 1.9. And the first step that we do is to deploy a new set of control planes at a newer version, let's say 1.10. It's a different color green, which is really useful to differentiate from the previous version of Istio. So the next step, what we do is to upgrade the namespace label right here to change the Istio color from blue to green. And because we enable Istio on the entire bar namespace, it means the Istio sidecar proxy will be auto-injected for all the Kubernetes pods. And what we do here is to do a rolling restart of our deployments, stateful sets, or daemon sets, so that all the pods in this namespace will be restarted and also have a new version of Istio injected. And because the namespace label select Istio green control plane, it is the newer version of Istio-D that's doing the injection, and also it is where the sidecar proxy connects to. And notice what's important or interesting is that between the two different namespace, foo and bar, even though there are different versions of Istio proxies running, they are still connected to each other. And this is really helpful for us to validate the Istio or the new version of Istio we want to upgrade to, because we could separate a pair of client and server in the blue and green service meshes. And by doing so, we can validate the interoperability of the two control planes, which is a prerequisite for quick rollback if the new 1.10 Istio is malfunctioning. So this is a really nice property. And the next step is to do the same on the another namespace. Once we do the validation and show that Istio 1.10 is working nice and it can interoperate with Istio 1.9. And the namespace sort of update is also by updating the label selection and restart all the a rolling restart of all the pods in the namespace foo, so that the Istio proxy is injected with a new version and it connects to the new control plane. And lastly, we just deprecate and remove the old blue control plane, and everything is now running at 1.10. So a couple of notes on this upgrade implementation. The blue and green Istio-D, or the control plane here, needs to have a common root of trust in order for us to achieve interoperability. The reason is that we require strict MTLS for all the mesh internal services. So the foo namespace and bar namespace that I just showed you before, they are all running within the Istio mesh, and their communication is through MTLS. And Istio-D signs the proxy certificates. So that's how, because in MTLS mode, both the server and the clients has to present certificates to validate their identity to establish trusts before any communication happens. And those certificates are signed by the control plane. And now if we are running two sets of control planes, they need to share the same set of trust in order for MTLS to still working. And this can be done by using either the same issuing CA or signing the issuing certificates used by the Istio control plane by the same root CA. So either approach is fine. It depends on your infrastructure or whether you have a dedicated private key infrastructure in-house at your firm. So second note on Istio upgrade is that during the upgrade, the behavior of how external traffic is routed to our mesh internal services is also changed. Recall that the external traffic is terminated at the Istio ingress gateways, and the gateways are provisioned by the Istio operator. Istio operator is part of the control plane and is a open source component that just allows us to describe our Istio control planes in the descriptive, declarative mode, and then the Istio operator will just make it happen by deploying the corresponding Kubernetes resources. And because it's two sets of Istio gateways, that means we need to drain the client traffic from Istio blue to Istio green before we can delete Istio green. So make sure that no more traffic is routed to the old gateway pods. And because the Istio ingress gateways in the two separate Istio namespaces are fronted by different load balancers with different IP addresses, it just means that we need to update the DNS records for our ingress host names so that we can route traffic to the new sets of ingress gateways. And the way to do that for us is to use external DNS, which is an open source project to manage public DNS records based on some Kubernetes annotation. And also we grant some service annotation to select both the service and also integrate with the external DNS. This approach is helpful, especially when we're running in a multi-cloud environment. It means external DNS sort of extract away the cloud-specific API or interface for managing the cloud provider-based DNS records. And from the perspective of a Kubernetes user or Kubernetes operator, it's just the same annotations from external DNS, which would provide a cloud agnostic abstractions and helpful when we're building toolings on top of external DNS or just orchestration toolings for the Istio upgrade. Brian, can you tell us more about our FedRAMS and ARM64 images challenge?
Yeah, absolutely. Go ahead and go to the next slide, please. Okay, so we have many different environments that we operate Snowflake in. We talked about early on. We run them in different regions, and some of these also include government-related regions where we have stricter encryption requirements to achieve different levels of FedRAMP certifications for running Snowflake services within those environments. And additionally, which is a slight aside from this, we also have different use cases where we would want to run our Kubernetes services on different architectures. So typically we run everything on AMD 64 architecture worker nodes. But there's also use cases now, not only for cost effectiveness and speed, but also for applications to run on ARM worker nodes, which is becoming very popular as of late. Unfortunately for both, Istio does not produce images for either of those use cases. So it was a challenging and interesting experience for us to have to figure out the build process of how to actually build Istio, the Istio proxy, Istio D, etc., and produce those images for us. And specifically in the case of ARM, produce a multi-arch image so that regardless of the worker node that we're running on, we can pull down the correct architecture image for our applications to use for Istio proxy on the fly. So we'll go ahead and talk a bit briefly about what that actually looks like to build your own Istio image. Can you go on the next slide, please? So specifically for FedRAMP, you have the Istio D images and Istio operator images are written and built in Go. And to actually build the compile a Istio image which has the correct cryptography libraries enabled, you have to actually build your own custom Go image. There's one that we have built internally, which is used to actually compile all these artifacts. And it's actually used as the source of building a handful of other images. So there are several different steps you have to go through to build your own Istio images. One is actually building the image which is used to build other images, funny enough, or which is this tools image. And within this tools image, we use this Go image that I just mentioned to build all the other Istio binaries. Similarly, we would do the same exact thing for ARM, for building our own ARM Istio images, except you would run those on different ARM architecture worker nodes. You can try to use features within Docker to emulate building on an Intel node for ARM, but we found that this is way too time consuming, and it's faster to actually just to spin up a dedicated ARM worker node to build that particular architecture. Fortunately, newer versions of Docker know which architecture to use when you're referencing images upstream within your Docker files. But I would call out that one dependency that Istio does have now is DockerX, which is a variation of the Docker CLI, which is used to basically dynamically pick up these architecture images. There's a bunch of other different flags you can specify of DockerX that aren't available with Docker. So that's just something worth calling out. So once we have actually built these tools images, there's one that's built for Istio proxy, and then there's one that's built for building like Istio D and Istio operator. We've gone ahead and always chosen to build Envoy first. The first couple times I built Envoy, I think it took well over 2 hours on some smaller instances. So one thing I could call out is to use if you have the capacity to, the larger instance types, and specifically CPU intensive nodes, because it can be quite time consuming, and if you have not perfected all the right steps after the fact, you may have to rebuild all over again, and that can just eat up a lot of your time. Since Envoy is built using a Docker image, the actual Envoy artifact, regardless if you're building ARM or a FIPS compliant image, is within the Docker image that was used to build Envoy. So you actually have to copy this onto your own host file system, so you can retrieve that later when you're actually building the Istio proxy image. Can we go to the next slide, please? Okay, and then finally, after we built the Envoy, we can go ahead and build a bunch of different Docker images. So Istio D and Istio operator have their own base images, which are built from Istio itself. They are, because Istio supports different distributions, like you can run in distroless or just a standard base. I believe there's also a CentOS 7 base distribution you can build. You have to build these base OS images. And again, there's nothing special really you have to do here for FIPS or ARM, except for ARM, you have to build them again on ARM worker nodes. Specifically for Envoy, it has some custom additional steps you would do. I mentioned copying the Envoy artifact to your local file system. You can actually reference that artifact prior to building the proxy image via this environment variable. And then lastly, you can build all the other different components as standard. One thing that actually did catch me early on when you are starting to use ARM is you need to make sure that the Istio components are configured to be able to be schedulable on ARM, because they typically aren't by default. And these can be overwritten via the Istio operator, or you can patch those resources on your own if you need to, so they're actually schedulable on ARM. I did not call it out here, but when you're building your ARM image, what we've actually done is provided 3 different flavors. Well, actually, it's 2 different flavors of Istio. One is a single standalone multi-arch image, which has references to both the upstream Istio image for Intel, and then the ARM image, which we have built in-house. And when we provide that to our Istio configurations, we just reference that image. For for government environments, we actually have built we produce a different image tag just for the FIPS enabled images, and yeah, I think that's all I could think of right there. For one thing, I guess one other thing to call out that we did try doing is producing a multi-arch FIPS image, but unfortunately Envoy right now does not produce the boring SSL libraries in ARM, which is the boring FIPS certified libraries in ARM. It's only supported in AMD 64. So that's why we have this split off between Intel and FIPS images and a multi-arch image. One other thing to note for the FedRAMP images is that there are commands, and I'm sorry I did not attach it here, that you can run through your, once you've produced an image, to basically see via a CLI output that you have a FIPS certified image. The version that will be produced by Envoy via the version command will be different than the standard distribution without the FIPS certified cryptography libraries. If you are interested in more details, the AWS Graviton guide is a great starting place to see how you can build the ARM images yourself. And fortunately, the FedRAMP steps aren't too much different, besides using a different base image with your the Go cryptography FIPS enabled cryptography libraries enabled. And I think that's all I have on this particular topic.
Yeah, well, I guess before we go, we would love to tell you more about our future roadmap and some of the interesting features that we think would be super useful to be a Istio add-ons to our platform. One thing is zero trust identities and MTLS gateways. And well, we do run MTLS within our clusters right now, but not for clients or services that's meshed external. And if you recall from my limiting speech, the service header, the custom HTTP header that we added on the client side is actually very collaborative. And that means we trust our clients to name and identify themselves correctly. But as you can imagine, that leaves rooms for a malicious user to just use the service header incorrectly to gain more privileges. And MTLS or stronger identity schemes can mitigate these issues. And that means we can just verify the client identities. And also Istio allows us to enforce RBAC policies through authorization policy, custom resources to implement RBAC access control for any services that's running within the Istio mesh. And we also want to streamline our Istio upgrade experience. Right now, we do have a set of toolings to make it easier, but it does require our operator to connect to a specific cluster and then run the set of CLIs that we have. That is helpful when we have like 20 or 30 clusters, but now at the current state that we run, it becomes tedious and also kind of error prone. It's possible that the operator could mistakenly connect to the wrong cluster and just that's a chance for disruption for sure. So having end-to-end automated Istio upgrades would make the upgrade experience nicer and safer. And next, we want to explore multi-cluster Istio. Historically, this hasn't been a top priority because of how our product architecture works. We just don't have a lot of cross-cluster traffic. All the components and services that Snowflake needs to operate its product is running within the same cluster. But as we grow as a company and as we onboard more and more engineers, we're building more internal tools and services that can be just internal facings, and they might live on different clusters. And now this multi-cluster needs is getting stronger, and we would love to support our users on this front and also integrate it with all the nice bits of Istio like MTLS and RBAC, rate limiting and all that. This service discovery, metrics, etc. And also on this internal systems or tooling or multi-cluster topic is distributed tracing. Because of more and more systems and also a longer callback chain, if you will, of the microservices world, it becomes necessary to have the distributed tracing to help our users understand when they get a connection resets, who exactly is sending that reset packet, which service down the line is having trouble right now that is ultimately facing this failing this particular requests. And having this distributed tracing allows us to correlate multiple microservices at once. And then we can dive deep into the logins and other monitoring systems, which allows us to more effectively troubleshoot any production issues. And with that, I want to thank you again for your time, and thank you so much for listening for our Istio topic here.
I really like to ask you one thing. I'm really interested in that. What has been the most challenging for you with working with multi-cloud, for you personally?
For me, I think it's mostly the feature disparity across cloud. There are moments like Brian has mentioned, we are exploring the different cloud-based load balancer offerings. It seems to be a very clean solutions if we can just use the Kubernetes pods directly as the backends, but that's not a feature that's available on all the cloud providers. And you was at least for myself, I see this sort of disparity happens in several places, like how we manage RBAC or IAM policies. For example, on GCP, the DNS records cannot be managed on a per record basis. The permissions is only per project. And that creates additional troubles on how do we limit the external DNS privileges and making sure that it doesn't mistakenly updates DNS records of a different cluster, for example. And yeah, trying to build a cloud agnostic platform or architecture our systems to be as cloud agnostic as possible is a challenge that we face, and an interesting ones, because the cloud provider also have their own roadmaps and it's adding new features. So,
Absolutely.
So the disparity that we see today might not be true tomorrow. But yeah, anything you want to add, Brian?
No, I think you hit the nail on the head, Charles. Often the problems that I have faced are nuanced differences between implementations between providers for the similar services. Like as you mentioned, specifically, load balancer has been a tough point for us lately, I think, in terms of the feature gaps that may be apparent across different providers, and making sure that it's a weird thing because Kubernetes does provide a similar construct to define how you would expose your services, but under the hood, really, the implementations are quite different between the different providers, and actual expectations you have end up being different. So that has definitely been a challenge, and has led to surprises and bit us before, where we thought we would have similar experiences with like connection termination, for example, across different providers. And we have to account for that and either come up with a different way of going about it, or I think that's probably the best thing I could think of at the moment.
Yeah, and I think this challenge is also true for our user as well. So despite our best effort of providing a cloud agnostic abstraction through Kubernetes, the application developed or deployed to this container platform still has to be cloud provider aware, mostly because they have to use the cloud specific client libraries to interact with object stores or key management service. And that API call in particular is very hard to be abstracted away. And that, in my opinion, is an open questions in this multi-cloud challenge in communities. And we would love to hear from you. How do you solve multi-cloud at your companies or projects, especially in a application level?